magnetic bodies do not reach the surface of the Earth, so their properties have to be determined by remote techniques. The problem of mass and other properties determination from observational data remains unresolved despite the long history of meteoroid studies. A model describing the interaction of small meteoroids with the Earth's atmosphere is applied to observations of Perseids meteor in order to reproduce the light curves and to determine the parameters of meteoroids. A model describing the interaction of small meteoroids with the Earth's atmosphere is applied to observations of Perseids meteors in order to reproduce the light curves and to determine the parameters of meteoroids. In this model, the mass loss of meteoroid is determined using the saturated vapor pressure of the arsenic meteoroid's substance. Dependence of the vapor pressure on the temperature for the some subjects are different according to various authors that affects the determination of the meteoroid parameters. An automated method to estimate the physical parameters of a meteoroid by comparing observational and model derived data with known parameters was suggested. A series of observing comparings were carried out during Perseids activity in the period 2010-2016 from South Greece. Part of this data with brightness smaller than -2 was considered. Panels on the table demonstrated application of different pressure dependence in the model. With dependence slightly affects the mass estimate, the scatter is less than 10%. More pronounced effects occurs for radius estimate. The scatter reached 55%. In terms of density, the spread may exceed 5 times. The choice of depends for the saturated vapor pressure strongly affects the shape of the light curve, the quality of its approximation, and the estimation of density. A porous body model was developed in 2 modifications. Porous model P1. The meteoroid consists of spherical particles in a square or rhombic skating. The particles themselves are mineral matter. In porous model P2, the meteoroid consists of spherical clusters which consist of particles of mineral matter. The clusters themselves are arranged in a square or rhombic arrangement and occupy half of the volume of the meteoroid. The picture shows solutions for 3 models, solid and 2 porous. Light curve is fitted differently. The porous body model has little effect on the mass estimate. Spread is less than 15–20%, more influence on size estimation up to 25%. The density estimate increases up to 2 times. These patterns are valid for both models, P1 and P2. The figure shows result for porous model P1. The density estimate increases in porous model and weakly depends on the residual function. These patterns are valid for both models P1 and P2. As for solid model vapor pressure, dependence significantly affects the shape of the light curve, the quality of its fitting, and the estimation of density and porosity. The density of meteor particles are estimated from observational data by various methods, and these densities vary over a fairly wide range. Here are some estimates obtained from the data of optical meteor observations and an estimate of the average density of comet Churyumov-Gerasimenko and the density of its dust particles. Our estimates are comparable with these values. There are empirical dependencies for determining the mass of a meteoroid by absolute magnitude, taking into account our parameters. They are based on a generalization of meteor observations. Parameter is included.
You have 5 minutes left.
Parameter is used to classify meteor bodies by the shape of the light curve. Observed light curves of meteors under consideration are characterized by F parameter 0.16, 0.53. Their maxima are in the middle of a shifted towards the beginning of the light curves. Fragmentation is not included in our model yet, so meteors with F parameter large 0.4 are fitted better. The slide shows our mass estimate and shows all other authors. The mass estimates we obtained are closest to the estimates based on VIDA, and difference by a factor of up to 5, given that these estimates were obtained at a luminous efficiency of 5%, at a luminous efficiency of 1%, the mass estimates would urge with the relationships from VIDA. The choice of dependence for the saturated vapor pressure strongly affects the shape of the light curve, the quality of its approximation, and the estimation of density and porosity. The average porosity for all meteoroids is dependent on the choice of saturated vapor pressure and range from 44 to 86, which is close to the values for IDP and to the porosity of the comets. The density of meteoroids is determined with a large correlatively along the obtained density values are close or lower than the results of other authors for Perseids. The estimate of the average density in the case of porosity body model turns of the higher than the solid body model.